Hello everyone, welcome to our discussion of section 5.3 where we will be talking about evaluating definite integrals. Now we've already looked at integrals or the antiderivative and their conceptual meaning with respect to the net area above and below the x-axis and under a curve. And we've also looked at the meaning of the integral in respect to the Riemann sum. Those were the main topics in sections 5.1 and 5.2, so we can get a feel for what integrals actually do. What is it that they're calculating conceptually? Now here, we will begin our review of a set of techniques that make finding integrals very easy. These are a certain number of formulas we will apply in this section, but the number of formulas is not limited to this list that we will go over in this section. In fact, in the back cover of your textbook, you will find about 100 different formulas for integration. Not all of those, well, in this course, we will use just the ones that we introduced today, but the rest of those formulas that you see inside the back cover of your textbook, a lot of them are used in Calculus 2 and especially in Calculus 3 and beyond. So those are extremely useful and make integration of very complex functions very easy and timely to do. So just a quick recap of definite integrals is what you see on the screen, which is if we have some function f that is continuous on some closed interval ab. So continuous meaning there are no gaps, jumps, or cusps along the function. And we've learned so far that's essential for the calculus methods to work. The functions must be continuous. And then, given that, the capital F denotes the antiderivative of that function f between these two limits. So this, what makes this integral definite, a definite integral, is the lower and upper limits that you see for this integration symbol. So basically, if we want to integrate a function, we will find the antiderivative of this function, in this case generalized as capital F, and then evaluate this antiderivative first at the upper limit. Whatever value we get, we subtract the value of the antiderivative evaluated at the lower limit, and we get a single number. As we said before in the previous section, this value could be either positive or negative. Now, just a quick recall that the main difference between definite and indefinite integrals is that definite integrals lead to a number, a single number, but indefinite integrals lead to a family of functions that are distinguished from each other by a single constant, because we have infinitely many constants possible for the antiderivative. Therefore, we say that this is a family of functions. So indefinite integrals lead to a family of functions. Definite integrals lead to a single number. Okay, having had that in mind, then let's look at a few of the formulas for integration that make integration easy to do. So let's call these table of indefinite integrals. Okay, and just so that we remember that this is not all of them by any means, this is just a fraction of those formulas. Let me just insert here table of a few indefinite integrals. Okay, so let's begin by introducing the first formula. So suppose we want to take the integral of some variable to some power dx, then this is easily done. We've done several of these before, but we just listed here. We add 1 to that power and then divide this whole expression by the new power. So in other words, x to n plus 1 divided by n plus 1 plus c. Okay, and we make sure that n is not equal to -1. That is to guarantee that we're not going to have a zero denominator here. That's all. Okay, so that's one of the formulas we have. We will list a little over a dozen of these formulas for this section. And then here is the easiest of them all, the integral of, and notice, by the way, that these are indefinite integrals, right? There are no lower and upper limits, but we can apply the same formulas to definite integrals as soon as we put the lower and upper limits, and then we won't use the c anymore. Okay, that's the only the difference. But we can use the same formulas for both types of integrals. So the integral of the natural exponential function is, of course, itself, right? E to the x plus c. Then the next formula, we have the integral of sine of x dx. Of course, we know that cosine of x has the derivative sine of x, but if derivative minus sine of x, but because this is positive sine of x, so then the antiderivative must have had a minus in front of it. So minus cosine of x plus c, again, because we're dealing with indefinite integrals here. Okay. The next formula is if we have the integral of secant squared x dx, that is equal to the antiderivative of this is tangent x of tangent of x plus c, of course. The next formulas, or the formula, is secant x, integral of secant x, tangent x dx is equal to secant x plus c. Okay, so all of that has the antiderivative secant x, and vice versa. The derivative of this is secant x times tangent of x. Okay, so the next one is 1 over x squared plus 1 dx is equal to inverse tangent of x plus c. So isn't that neat? 1 over x squared plus 1 has the inverse tangent as its antiderivative. Okay. And then the integral of hyperbolic sine of x dx is equal to the hyperbolic cosine of x plus c. Okay. Next one is the integral of the hyperbolic cosine dx is equal to hyperbolic sine ex plus hyperbolic sine of x plus c. Okay, so these are a few, and then let me put the rest of them on this side of the page. I want to list them on the same page so they're easier to reference when you're solving or studying this page or this section. Okay, so I'm just going to put a divider line here, another one right here, and another one right here. Okay. Okay, so in the next one, we have the integral of some constant times a function, constant c times a function f of x dx is equal to, the constant can be brought outside and in front of the integral times whatever integral we have. And that's true for all integrals. The constant that is on the inside multiplying by everything else can be brought out, just like that. The integral of 1 over x, this is another one of my favorite ones because it's very easy to remember and use. The integral of 1 over x dx is natural log of x plus c. Okay, of course I have to also put a c here because we're dealing with a definite indefinite integral. Since we have a c here, I'm just going to correct myself and say this should be d. So let me choose another letter. So let's go, but that's just denotes the constant, which is c. That's that constant. Okay. All right, so here is another integral, very, very useful integral. These are the most common integrals that you come across in Calculus 2 as well, but some of them you encounter a lot more than the others. That's one of them, this is one of them, and here's another one which you come across a lot, especially in Calculus 3 as well as Calculus 2. That one, if you have the exponential function dx, the antiderivative of that is the exponential function itself divided by the natural log of the base term. So natural log of a, and then of course plus c. Okay, very useful. And then another integral would be integral of cosine of x. We talked about sine of integral of sine of x, but not this, but this is just as easy as that. Integral of cosine of x dx is equal to sine of x plus c. Integral of cosecant squared x dx is equal to minus cotangent of x plus c. Right? This is another useful one. Integral, or the antiderivative of the cosecant squared is just minus cotangent of x. And then integral of cosecant of x cotangent of x dx is equal to minus cosecant of x plus c. Okay, one more. We're not done with this, but they make our life easier when we calculate the integral of some expressions. So let's get them all in here. 1 over, move this up a little bit, 1 over square root of 1 minus x squared dx is equal to inverse sine of x plus c. All of these are very useful integral formulas, and I'm glad that we are introducing them in this section, especially for those of you who will move on to Calculus 2 and beyond. Please make sure that you get plenty of practice with applying these formulas. Okay, so now that we've introduced these formulas, let's actually use them. So in this example, we would like to evaluate, or in this series of examples, we want to evaluate the following integrals. Okay, so here's the first one. Let's call it A. We want to, and of course these are all definite integrals. So we want to evaluate the integral from 1 to 2 of 4x cubed minus 3x squared plus 2x dx. Okay, this is an easy expression to integrate because all we have to do with these power functions, with each of them, we add 1 to that power and divide the expression, that expression by the new power. Okay, so let's do that. So we have, oh, by the way, please remember, and I'm counting on you that you do this, when I write an example down, please pause the video. It's so easy to do, and it will benefit you tremendously if you first write down your own thoughts before you look at my solution. I mentioned this to all my students. My solutions are really worthless if you're just copying them down. So most important solutions here are your own solutions, and because they come from your thinking and your own developing of your thinking. And so when you see my solutions, then use them just as a way to compare and correct your own solutions if necessary. Hopefully our solutions agree. Okay, so as we said, we want to add 1 to that power and then divide this expression by the new power, which is 4. And we'll do this for the other two as well. So 3x cubed, divide this by 3, plus 2x squared, divide by 2, and then 1 to 2. Okay. And then, so let's simplify. Of course, we can simplify. So x to the 4th power, this and that cancel each other out. Minus 3's cancel out, we end up with x cubed. Plus the 2's cancel out, we end up with x squared. And going from the lower limit 1 to 2. So now, the way we evaluate this, like we said in the beginning on the first page here, so what we do, once we have the antiderivative f, then we evaluate the antiderivative at the upper limit. Whatever we get, we subtract the value of the antiderivative calculated at the lower limit. Okay, antiderivative at the upper limit minus the antiderivative evaluated at the lower limit. It's pretty straightforward. Okay, so let's do that. Let's plug in this expression, in this antiderivative, with 2 and then subtract by substituting 1 into that expression. So here's what I mean. So, and I hope this so far agrees with what you wrote down on your scratch paper before you came back to this video. So we have 2 to the 4th minus 2 cubed plus 2 squared, right? Minus, I just plugged in 2 for that. Minus, now we have to plug in 1, the lower limit in all of these. So 1 to the 4th minus 1 cubed plus 1 squared, right? Like that. Okay, so then let's calculate all of this. We have 16 minus 8 plus 4 minus 1 minus 1 plus 1. And then we have to distribute that minus, and when we do all of that, so 16 minus 8 is positive 8, plus 4 is 12, and minus 1, because these two cancel out, minus 1, it's just 11. Okay, so here's our final answer. As we mentioned, any definite integral leads to a number. Okay, and there we have it. Let's go over the next example. We have plenty examples coming up. Please don't forget to pause the video once I write down the example. Minus 1 to 1 are the lower and upper limits of t times 1 minus t squared dt. Okay? So I'm assuming that you've already solved this and you're back. So the first thing I would do is just expand this binomial squared so we can then distribute this and make it easier for ourselves. So we have then integral from -1 to 1 of t times 1 minus 2t plus t squared dt. Okay, so that's what we have. And then let's distribute. So we have integral from -1 to 1 of t minus 2t squared plus t cubed dt, and then t squared. So now add 1 to this power, divide by the new power. So this is what we get, minus 2t cubed over 3 plus t to the 4 divided by 4, of course, evaluated from -1 to 1 limit. Okay, so now let's plug in for t with 1 and then subtract whatever we have from, and then we will plug in -1 into t and subtract that from that quantity. So when all is said and done, this is what we should get. 1/2 minus 2/3, and then plus 1/4 minus, this is pretty straightforward, right? Just plug in, you get that. Then minus, then plug this one in, and you get 1/2 plus 2/3 plus 1/4, and then after you take the common denominator, simplify, hopefully you will get the same answer I have, which is minus 4/3. If you don't get it, the same answer and you have questions, I'm counting on you that you will let me know. Okay, so here's another one like that. Okay, so next example. Suppose we want to integrate this expression from 1 to 4, square root of y minus y divided by y squared dy. So the easiest thing for this, before you pause the video, I guess, is my hint to you is convert everything to powers. Get rid of this square root, instead use y to 1/2 power, and then combine the like powers, and then go from there. Okay? And hopefully, once you're done, our answers agree. Okay, so I'm assuming you've done that, and now you're back. So integral from 1 to 4. And first thing, I would separate these over y squared. So square root of y over y squared minus y over y squared dy. Okay? And then let's convert this to power, rational power, y to 1/2, and then subtract this power from it because the bases are the same. So 1 to 4, integral of y to minus 3/2, that's what I did. So 1 minus 2, you get minus 3/2. And then also minus 1 minus 2 would give us minus 1 dy. Now this one is fine, but this one, let's rewrite it back in a fractional form. And after I do that, I'll show you why I'm suggesting that. So I'm just going to keep that as a power, y to minus 3/2 power, and then minus 1 over y dy. The reason we want to do that is because one of these formulas that basically the idea here is that as things get complicated, we want to write things in a way that look like the formulas we have, because if they do, then we're going to be able to use these formulas and integrate these expressions very easily. So 1 over x, the integral of 1 over x dx is simply natural log of x. So very easy to do. That's what we have here. 1 over y will have the antiderivative of natural log of y. Okay, so let's do that. We have then integral from 1 to 4 of, so add 1 to this. This is minus 1.5 basically. Add 1 to it, you get minus 1/2. Divide this expression by minus 1/2, you get minus 2. So we get minus 2. We don't really need the integral. So I will get rid of this. I will white out this before posting these notes on Canvas. So we don't need the integral symbol anymore. We can directly go to our integral or the antiderivative. So we have minus 2 y to minus 1/2 power. That's after we add 1 to it and divide by the new power. And of course, we have minus natural log of y. Okay, this whole thing goes from 1 to 4. Okay. All right, so if we stretch this a little bit or simplify it, we get minus 2 over square root of y, right? Just rewrite that as a square root of y minus natural log of y from 1 to 4. Okay. All right then. So here then substituting 4 in this expression, then minus substituting 1 in that expression, this is what we have. So we'll get minus 2 over square root of 4, and then minus natural log of 4 minus, so substitute 1 then, minus 2 over square root of 1 minus natural log of absolute value of 1, which is 0, right? So I should have used my red ink here like that, and then like that. So this is just 1. Okay, and that's the absolute value like that. Okay, so we get, from here, we get minus 1. Minus 1 minus natural log of 4, or absolute value of 4. We can keep it in exact form. We can calculate this in decimal form, but let's keep it in exact form. It looks better that way, and it's exact. And then minus 2 minus 0, right? Like that. So then we have 1 minus natural log of 4, like that. Okay, that's the final answer. All right, so continuing with our examples, we have part D here, integral from pi over 4 to pi over 3 of cosecant squared theta d theta. Okay, so from our table of integrals, we know that the integral of cosecant squared x is minus cotangent x plus c. Okay, so let's say recall, and again, I'm hoping that you've already solved this and you're back to the video to see what I've done. So we know we know that integral of cosecant squared x dx is equal to minus cotangent of x plus c, right, for the indefinite integral. Now we won't need the c anymore, but we can use the rest of it. So therefore, then, for us, we have minus cotangent of x, or sorry, cotangent of theta in our case, right? This is the general formula. For us, it's theta, cotangent theta, and then this is from lower limit pi over 4 to upper limit pi over 3. Okay, so let's plug in. We have minus cotangent of pi over 3, which is the upper limit, minus cotangent of pi over 4. Okay. So what do we have here from the table of what we learned in Math 127? We learned about the table of common trigonometric function values. For pi over 3, the cotangent is square root of 3 over 3 or 1 over square root of 3, either one. So we can say then minus 1 over square root of 3, and then minus that's cotangent of pi over 4 is 1, with this minus 1, right? So we have minus 1 over square root of 3 plus 1. So you can give the answer either in this form, or you can say minus square root of 3 over 3 plus 1. Okay, you can, if you want, you can rationalize the denominator, which is what we did in Math 127. In Math 127, we didn't use that, or rarely use that. We use this form, the rationalized form. Okay, so next example. Suppose we have, and let's say this is part E, we have integral going from 0 to pi over 3 of sine of theta plus sine of theta tangent squared theta divided by secant squared theta d theta. Okay, like that. Okay, so when you get an expression like this, your objective should be to figure out a way to reduce this or simplify it to something that would be represented by one of these formulas. We definitely cannot leave this expression like this because it doesn't match any of the formulas we have. We need to get it there. We need to get this expression to look like something we have on that table of integrals. Okay, so where do we start? Well, first thing I think we all notice is that we have sine of theta in both terms. So let's factor it out and let's see what happens. Okay, that's the most obvious thing that we can see we can do as the next step. So we have the 0 to pi over 3 with sine of theta factored out. We end up with 1 plus tangent squared theta divided by secant squared theta d theta. All right. So now from Math 127, or our trigonometry class, we remember we had 3 squared identities. Remember those, the 3 squared identities? This was one of them, right? So let's recall. So recall from Math 127 that 1 plus tangent squared theta is equal to secant squared theta, right? That's one of the squared identities. So let's for this expression, let's plug in with its equivalent secant squared theta, especially since we know there's a secant squared theta in the denominator. So right away we can cancel things out. So this is looking good for us. After we factored out, things started to look good. Okay, so let's do that. We have integral from 0 to pi over 3 sine theta times that secant squared theta divided by secant squared theta d theta. Okay, so we know that we can cancel these two, and we end up with a very nice and simple expression to integrate, which is integral from 0 to pi over 3 of sine of theta d theta, right? That cosine of x is the antiderivative of sine, except that we would end up with a minus sine of theta. So the fact that we have positive sine of theta means that the antiderivative must have been minus cosine of theta going from 0 to pi over 3. Okay, that minus should be there to give us the positive sine theta as the derivative of this antiderivative. So the next step, of course, is just plug in. So we have minus cosine of pi over 3 minus cosine of that minus cosine of 0. And so we know that, so this will be like that. So cosine of pi over 3 or 60 degrees is 1/2, and minus times that is minus 1/2. And then minus cosine of 0 is 1. So we end up with positive 1/2. Okay, like that. Okay, so let's go over the next example. So that was part E. Let's call this part F. So suppose we have the integral from negative 10 to 10 of 2e to the x, the natural exponential function, divided by the hyperbolic sine plus hyperbolic cosine of x dx. Okay, this is really interesting because so here we have a natural exponential function which, as we mentioned earlier, has a derivative that is itself the easiest integral we can have. But then in the denominator we have these the hyperbolic sine and hyperbolic cosine. So back in section 3.6, when we talked about hyperbolic functions, so let's recall again. I hope that you've already paused and you've done your own work on this. So recall from section 3.6, which has to do with hyperbolic functions. That hyperbolic sine of x is equal to e to the x minus e to the minus x power divided by 2, and hyperbolic cosine of x equals e to the x plus e to the minus x over 2. These are very interesting equations for hyperbolic sine and cosine in terms of the natural exponential function. If you ever have to take the course called complex analysis, which is a very interesting math course, it's a senior level math course, you'll be dealing with these two forms of the hyperbolic sine and hyperbolic cosine for the whole semester. And of course, hyperbolic tangent would be this divided by that. So it gets really, really interesting. But so now, in order to get everything in our expression to perhaps look like the natural exponential function that we have, which has a very easy antiderivative, let's plug in for these two with their equivalents in natural exponential function. So let's do that. So I have, let's do it here. We have, this is going to be a big fraction here, minus 10 to 10. And so 2e to the x divided by, make sure that, and then all of this replaces that. So it's going to go off the screen, but it's okay. You'll have it on the lecture notes anyway. So e to the x minus e to the minus x over 2, then plus the hyperbolic cosine, plus all of that, e to the x plus e to the minus x over 2. Okay, oh, of course, I have to remember dx here. All right, so now this is just a complex fraction. We have plenty things to simplify here. You can see right away because we have already the common denominator, so we can add and subtract what we have in the numerator. We can quickly do that right away. So we have 2e to the x in the numerator. In the denominator, what do we have? These two guys, this is minus e to the minus x, this is positive e to the minus x, so these two cancel out. Then we end up with e to the x plus e to the x divided by 2, right? So 2 e to the x, that's this plus that, divided by this, the common denominator. Of course, dx, let me not forget that. So look at the denominator. Everything here, most things simplify here, right? So this 2 and this 2 cancel out. And then we end up with 2 times e to the x over e to the x. Then e to the x terms cancel out. So we basically end up with integral of 2 dx going from negative 10 to 10. Okay, so this has a very easy antiderivative, of course. So 2x, right? 2x. Compare what we have with what we started with, right? And look how much these formulas made the life easier for us. Okay, we just plugged in and everything simplified. So we have antiderivative is 2x going from negative 10 to 10. Okay, so let's calculate this. We have 2 times 10 minus 2 times minus 10. So we end up with 20 and plus 20 or 40. And here's our final answer there. Okay. Another example. Suppose we have the definite integral from 0 to square root of 3 over 2 of dr over square root of, let me bring this down, square root of 1 minus r squared. So dr is right here, right? Okay. Now, if we look back, this looks familiar. If we look back at our square root of 1 minus r squared, that looks awfully like this, or identical, right? With the exception that instead of x, we have r. And instead of dx, we have dr, right? But that's the same thing. The integral of that is the inverse sine function. Great. So that's all we needed. So recall, I hope you paused before you see my solution. I hope you paused. Integral of 1 over square root of 1 minus x squared dx equals inverse sine of x plus c for the indefinite integral. Of course, here we don't need this c. All right, so let's apply it. We have then, so this would be equal to the inverse sine of r going from 0, where r goes from 0 to square root of 3 over 2. Okay? And then that will be inverse sine of square root of 3 over 2 minus inverse sine of 0. So sine of what angle is square root of 3 over 2? For sure, not pi over 6, right? Sine of pi over 6 is 1 over 2. So it should be pi over 3. So this is pi over 3 minus sine of what angle is 0? 0. So we end up with pi over 3 as the final answer. Another example would be, suppose we want to find the definite integral from 1 over square root of 3 to square root of 3 of 8 over 1 plus x squared dx. So once you solve a few of these, you'll notice that as soon as something looks familiar, you'll notice it very quickly. I mean, take a look at this. That looks familiar, right? 1 plus x squared in the denominator. Right here, 1 over x squared plus 1 dx has the antiderivative inverse tangent of x. Okay, great. So let's recall the antiderivative, the indefinite integral of 1 over 1 plus x squared dx is equal to inverse tangent of x plus c. Of course, we have definite integral, so we're not going to need the c. Okay, so then in that case, let's write this out. But we have an 8 here, right? We have an 8. So 8, and we had another formula here that any constant on the inside of an integral can be, which is being multiplied by the rest of the expression, can be brought out and in front. Okay, so that's what we had. My microphone fell. I hope it didn't cut out the voice, so hopefully not. So let's plug in then let's have that, but let's not forget that we have to multiply 8 by that. So we have 8 times inverse tangent of x integrated from 1 over square root of 3 to square root of 3. Okay, so then we have, that is equal to, we can bring the 8 out and factor it, and then calculate this function at the upper limit and minus that, the lower limit. So we have inverse tangent evaluated at square root of 3 minus inverse tangent, like that, evaluated at 1 over square root of 3. Now, tangent of what angle is the square root of 3? We know that from table of special trigonometric values from in Math 127. This was pi over 3. Theta pi over 3 has this tangent, square root of 3. And this one is really square root of 3 over 3 after we rationalize it, which is what we did in Math 127, and that will give us the angle pi over 6. So then the result here is 8 times pi over 3 minus pi over 6, or 8 times pi over 6, right? That pi over 6. So after multiplying and simplifying, we have 4 pi over 3. Like that. Okay. All right, so let's see another example. Suppose we want to integrate from pi over 4 to pi over 3 of secant of theta tangent of theta d theta. That also looks very familiar, right? This looks very familiar. So secant x times integral of secant x times tangent x dx is secant x. Very easy, right? So that's what we're going to do. This is equal then. So let's, so we can write this right away. And this is equal to secant of theta, which is our variable here, not x, from pi over 4 to pi over 3. And then if we plug in, we have secant of pi over 3 minus secant of pi over 4. Of course, this would be 1 over cosine of pi over 3. If you remember it from the special table of trigonometric values, you can write it. But I always like to convert everything to sine and cosine because those are the ones that I've memorized. I convert these to those, and then I calculate what these should be. And the same thing here, 1 minus cosine of pi over 4, because secant, as you know, is the reciprocal of the cosine function. So then we have, so this is 1 over, cosine of pi over 3 is 1 half, minus 1 over cosine of pi over 4 is square root of 2 over 2. And then after simplifying, so this first piece is just 2, and then minus 2 over square root of 2 after we simplify this complex fraction. Take the common denominator, what do we get? We get square root of 2 and 2 square root of 2 minus 2, right? And then factor out the square root of 2, and then we get 2 minus square root of 2 divided by square root of 2, and of course these two guys cancel out, and we get the final result, which is 2 minus square root of 2. Okay, so here's that. If you remembered what these were, secant that and secant pi over 4, you could really do this a lot quicker than I did. But anyway, I remember the cosine and sine functions. Okay, so then another example of this sort. Suppose we want to calculate the integral from 0 to 2 of an absolute value. So there, as I mentioned earlier, there are some formulas nearly 100 of them in the back of your textbook, and there are some integration for absolute values or integral of absolute values that have a formula that you can use. For things like this, however, the only thing we have to do, remember to do, is first apply the definition of an absolute value, which means, remember when in basic algebra, when we calculated or solved absolute value inequalities and equalities, the first thing we did, we applied the absolute value definition. So we're going to do the same thing here, but you got to remember that that will affect the limits of your integration. So let's see how that happens. But it's pretty straightforward after that. So recall from the absolute value definition, so that the absolute value of that expression is equal to 2x minus 1 if that expression is positive. So 2x minus 1 greater than or equal to 0. And it's equal to minus 2x minus 1 if 2x minus 1 is less than 0, right? That's just applying the definition of absolute value. So let's simplify this a little bit. What we get is this is equal to 2x minus 1 if, solve this for x, this inequality for x, we get x greater than or equal to 1/2. And then minus, let's distribute this minus. Let's not keep it out there. So we get 1 minus 2x, right, when we distribute this. Let me move this up. So distributing the minus here, we get 1 minus 2x if x, solve for x here, less than 1/2. That's what I meant when I said that this will, when you apply the absolute value definition, it will affect the limit, how you would calculate this integral. It will affect that, okay? So, because this one is saying if x is less than 1/2 all the way to infinity, which is, of course, we're not going to go that far, we have to stop at 0, then this is our expression. If we have, if x is equal to or greater than 1/2, then this is our expression when we integrate. Okay, so then, therefore, and I want to then, so we have to rewrite that integral, right? And I have to move this up, as you can see. Then that integral, which was 0 to 2 absolute value of 2x minus 1 dx, is equal to integral from 0 to 1/2, right? From 0 to 1/2, then we have that expression. 0 to 1/2, we have 1 minus 2x dx, right? Plus the rest of it, which is from 1/2 to 2, right? That's the upper limit. So from integral from 1/2 to 2, but I got to be careful because now that's my expression inside the integral. Not that, but this one, depending on where we are. Okay? Okay, now we got it. Now we can easily integrate this. So we have x minus x squared going from 0 to 1/2 plus x squared again minus x going from 1/2 to 2. Okay? All right, so when we evaluate this, what are we going to get? We're going to get, I'm just going to evaluate this. So 1/2 minus 1/4, right? Minus, of course, substitute 0, we get 0, plus substitute for x with 2, we get 4 minus 2 minus, right? 1/2 squared is 1/4 minus 1/2. So simplifying all of that, what we should get is 1/4. This is what I have. I hope this will match what you have, plus 1/4 equals, then after simplifying, we get 1 plus 8 plus 1 over 4, 5 over 2. Okay? Like that. All right, so another example. So suppose we want to integrate from 0 to 3 pi over 2 this expression, absolute value of sine of x dx. Okay. So given the previous example, you should be able to get this to the final answer. So please pause the video and attempt this and see what you end up with. And then if you come back, it'll be nice to compare your solution with this. So I'm assuming you've done that, and now you're back. So the first thing we want to do is that, because this expression, it says 0 to 3 pi over 2, and this is an absolute value. So we have to break this up, right? And you know when we do that, we're going to end up with two integrals, just like we did in the previous example. So recall, so applying the definition of the absolute value we have, so absolute value of sine of x equals sine of x. Well, let me draw a sketch here just in case. Maybe I can fit it. Maybe I can do it right here. It's just a small drawing. So if we draw, we did this a lot in Math 127. So if we draw a unit circle, let's say something like that, right? So this limit of integration is from 0 to 3 pi over 2. So 0 is here, this is 0, this is pi, and 3 pi over 2 is here. So we're integrating from here. I should have actually drawn it as a wave, but not as a wave rather than a circle. So we can still do that. It's no big deal. Because when you apply the definition of absolute value, you need to know from where to where it's negative and from where to where it's positive, right? Just like what we did here. See, if inside expression is greater than or equal to 0, then this is our expression. If that is less than 0, then this is our expression. So we need to know where sine that's what my goal is, to show here where the sign is positive and when it's negative. I'll show with my red ink here. So if we draw a sine wave like that, right, we know that sine function is 0 as 0 and pi, and then 3 pi over 2 will be right here. So sine function, sine of x, you can think of it as that circle too. So sine function is positive. The wave and the circle both work, but I think the wave would be more appropriate here. But anyway, from 0 to pi, the sine function, which is along the y-axis, is positive, right? 0 to pi. And if you look at the wave is also from 0 to pi, we are above the x-axis, which means the sine function is positive. From pi to 3 pi over 2, the sine function is negative because it's below the x-axis. And here you can see it on the unit circle. From pi to 3 pi over 2, the y-axis is negative, right? So if you want to use the circle or the wave, both will work. But the objective, of course, here was to show or to remember that the sine x function is positive from 0 to pi. So that, now we can apply the absolute value definition. So we have absolute value of sine of x equals sine of x if x is between 0 and pi. 0 and pi, right? We can guarantee that that function is positive between those two limits. And it's going to be negative if x is between pi and 3 pi over 2. Like that. Okay? So this will tell us how we need to integrate our original function. So let's do that. Let's set this up. Let's set this up with the new limits of the integration. I hope you don't mind. I have to scroll this up. Maybe if I zoom out a little bit, I can show more. So anyway, it doesn't affect much. So, all right, so let's break up this integral into, I'll just write it down again. It's no big deal. So here it is again. Integral from 0 to 3 pi over 2 of absolute value of sine of x dx is equal to integral from 0 to pi, right, of sine of x. 0 to pi dx plus integral from pi to 3 pi over 2 of minus sine of x. And I could put this minus up front too. Okay? All right, so like that. All right, so now we can integrate. Integral of this would be minus cosine of x, because it's going to give us positive sine of x, from 0 to pi, plus cosine of x as the antiderivative going from pi to 3 pi over 2. Okay. So let's plug in. We have minus cosine of pi minus cosine of 0 plus cosine of 3 pi over 2 minus cosine of pi. Like that. Okay. So cosine of pi is minus 1. Minus 1 times minus is positive 1. Plus cosine of 0 is 1. Minus 1 times 1 is minus 1 times minus, again, positive 1. Plus, so cosine of pi over 2 or any multiples of pi over 2, including 3 pi over 2, is 0. So we have 0 minus cosine of pi is minus 1. So what do we have? We have 2 plus 1, right? Minus 1 is plus 1. So we have 3. Okay. I hope these start to make sense and how easy it is when we have those table of integral value integrals that we can use here. Okay. So let's change the format of these examples a little bit. So here we want to calculate the area of the region that lies under the curve and above the x-axis. For this function, y equals 2x minus x squared. Really, the key here is what they're asking is lies the area of the region that lies under the curve and but above the x-axis. Those are really critical things to note there. So if we want to know the area under the curve but above the x-axis, we're going to have to graph this function or know at least where the x-intercepts are. But eventually we'll have to graph it anyway, so let's do it. So if we, the first thing we want to do is find the x-intercepts and basically graph the function, even if they don't ask us. Graph the function. So to do that, so then x-intercepts would be 2x minus x squared equals 0. This is, of course, easy to factor. Times 2 minus x equals to 0. So x would be equal to 0. So that's, and then x equals 2, or, 2. So from here, one intercept is the origin. The other intercept is 2, 0. Okay. In fact, if we graph this function, this is what we're going to get. So I think I need just a little bit of space here to graph that. Okay, that should be good enough. Okay, so if we increment here from 0 and then 1 and then 2, let's say, 1 and 2, these are our intercepts here and here, and let me try as best as I can to draw this. So I guess this would be also 1, so as high as it would get would be 1, so 2 minus, so this would be maybe if I put like that. Okay, so let me start from here, and I'll just do that, like that, and also on this side, like that. Okay, so the area under the curve would be all of, I mean, it would go down to negative infinity on this side, but they say under the curve and above the x-axis, right? So then we are limited to this area. to this region. That's the area under the curve, but above the x-axis. It goes from 0 to 2. So that's where we want to integrate over dx, right? That's dx along the x-axis. Okay, so let's set that up. Therefore, we have our integral will be from 0 to 2 of 2x minus x squared dx. Okay, so that's easy to integrate. As you can see, we have x squared and then minus x cubed over 3 from 0 to 2. And then, of course, let's evaluate that. We have 4 minus 8 over 3 minus 0 minus 0, right? So 4 minus 8 over 3, it is 4 over 3. Okay, positive 4 over 3. So that's that. Okay, let's do something similar to this again with graphing. So we have, suppose in here we want to evaluate to illustrate, and this time they ask us to illustrate with a sketch. Okay. Evaluate the integral. Which integral? Here it is. I should have written it up here. It goes from pi over 4 to 5 pi over 2 sine of x dx, right? All right, so that's an easy integral. So that would be minus cosine of x from pi over 4 to 5 pi over 2, right? So this would give us minus cosine of 5 pi over 2 minus cosine of pi over 4, like that. And 5 pi over 2, that's just 0, right? So we have 0 minus, that would be minus square root of 2 over 2. So we get, as a final answer, we get square root of 2 over 2, right? So they say, illustrate this with a sketch. Okay, let's do that. So we have the function we're integrating is sine of x. So we need to draw a sine wave, not a cosine wave, okay? It's just the function we're, I think that's what this question is trying to demonstrate, that what we're calculating with the integral is the net area between this function and the x-axis. So we need to graph this and see where those areas are that this integral then finds and obtains the net area by adding and subtracting these regions. Okay, but this is the one we're going to graph, not cosine. Okay, so let's do that. And then, so this is from positive lower limit to positive upper limit. I mean, so I'm going to give everything to the positive side. We don't have minus pi over 4 or anything like that. So all of this area, or all of this blank space, I will dedicate to the positive side, like that. Okay. So we start from 0, and I want to draw some guidelines for myself here because the sine function is pretty symmetric. So let's see. So if I take this as, let's say, 1, then I want to take an equal distance on this side as negative 1. So what would that be? That would be about an inch, almost exactly an inch. So I'll take off, I'll just increment almost exactly 1 inch on this side, right? And then I'll just draw a dashed line here so I can keep my lines to where they should be and not go beyond to where they shouldn't be. So that's that. So the dashed line is not necessary that I'm drawing. It's just to keep my drawing as accurate as possible. That's all. Okay, so then, since I have these guidelines now, then I can draw a sine wave going from, so let's start from here. We go up like that, come down and do that, and then go up like that again. Okay? So if I actually continue this like that, right? So it should curve back down again after that. So we know that from here to here, that's pi. From here to here is 2 pi. But that 5 pi over 2 is beyond 2 pi, right? Because if we had 4 pi over 2, we'd have 2 pi. But this is 5 pi over 2. So this goes additional, so 4 pi over 2 plus, so it goes another pi over 2 beyond that, which would be actually at which point sine function is 1. So right there is where it would stop. That's the upper limit of the integration. This is where we have 5 pi over 2. Okay? So then this quantity, square root of 2 over 2, which is the integral of sine x function going from pi over 4 to 5 pi over 2, is this region. So where is pi over 4, right? We need to find the net area between this integral, finds the net area under the sine curve, or between the sine curve and the x-axis, from pi over 4 to 5 pi over 2. We already know where 5 pi over 2 is, right? So where is pi over 4? Well, if this is pi, then this would be pi over 2 right here. That's pi over 2. But the lower limit of our integral is pi over 4. So that would be roughly here. So this is pi over 4. Okay? So we can then say that that quantity is the net area represented by this shaded region. Right? Notice I'm stopping at pi over 4 because that's the lower limit of the integral. Okay? And then that, of course, and then from here to here. Okay? So the net area, and if I can find my thick marker here, net area means, so we have a positive area here, we have a negative area here, and we have a positive area here. So if you add all these, the net area then is positive square root of 2 over 2. So it's less than 1. That's also worth noticing. Okay, it's a small quantity. All right, so let's look at another example. So suppose we want to find this time we want to find the general indefinite integral. Okay, not so we're going to have a c, a constant integral. So this is worth noticing. So let me indefinite integral. So we switched gears a little bit here. Integral of, notice the limits, upper and lower limits are missing, right? So we have an indefinite integral. Sine of x over 1 minus sine squared x dx. Okay. So I hope you pause the video and come up with a solution for this, and then come back and see what I have. So I'm assuming you've done that. So recall this denominator, it should remind you of one of the squared identities that we have, right? In trigonometry, we learned about those. So recall that sine squared x plus cosine squared x equals 1. Therefore, cosine squared x is equal to 1 minus sine squared x, right? That's what we have. So let's replace 1 minus sine squared x with its equivalent, which is cosine squared x. All right, so we're going to do that. So sine of x divided by cosine squared x dx. Now, we have to get this to somehow look like one of those formulas that we have, right? Right now, it doesn't look like, this does not look like any of these formulas that we introduced. I know this is not all of the formulas that we have, but for this section, we should have something that looks like one of these formulas. And right now, we don't. So what do? Let's break this up a little bit into two different. So let's break this up. So we have sine over cosine, right? So sine of x over cosine of x times 1 over cosine of x dx, right? So now we're getting something that is going to look familiar. So sine of x over cosine of x is tangent of x. 1 over cosine of x is secant of x dx. Or, let me rearrange this so you'll recognize this. Integral of secant x tangent of x dx. Does that look like anything we have here? It sure does, right? Secant x tangent x dx. What integral does this have? The antiderivative of that is secant x plus c. So we can quickly write down that this is equal to secant x plus c. Okay, very quickly we can get there. Let's do another example. This is a short one, so maybe I can include it right here at the bottom of this. So let's say this is part B of this, finding the indefinite integral this time. So we have sine of 2x divided by sine of x. I'm sure some of you, if not all of you, see how easy this is, right? If you remember the double angle, sine 2x from trigonometry, or from earlier in this course. So let's recall that sine 2x is equal to 2 sine x cosine x, right? So let's replace in an integral with that quantity. We have 2 sine of x cosine x divided by sine of x dx. Of course, on the inside, the signs cancel out, and we get integral of 2 cosine of x dx. So we know that that constant can stay just like that. So we have the antiderivative of this is simply 2 sine x plus c. Okay, so that's all there is to it. Let us go over another example. This is a bit of a word problem. It's not too bad if we give an example of these as well. Okay, so this one, it says in meters per second, along the line. And so here's the velocity function. Vt equals 3t minus 5, t between 0 and 3. And given that, they say find, for part A, they say find the displacement. And one thing I just want to make a note of is that and the part B says find the distance, okay, over this time interval. So displacement is a vector, so which you will see in well, you've seen a little bit of it in trigonometry, but you'll see it in a lot more detail in calculus 3. But displacement, because it's a vector, can be either positive or negative. So let me just make a note of that. Displacement can be positive or negative. But distance is always positive. And you'll see why this is important in this problem. Okay, so when do we have something that is always positive in mathematics? It's just when we have absolute value, right? So when you calculate the distance, you have to integrate an absolute value. But here we don't have to do that. We can just integrate over the velocity function. If you've taken physics, introductory physics course, or in other courses you may have seen that the integral, that the derivative of the distance or displacement function is the velocity function. And then the derivative of the velocity function is acceleration. And I'm sure you've seen that if you've taken the introductory physics course here at UNLV. So we want to do that, so let's integrate over this interval, 0 to 3. And this function, right? And it's t, so we have to have dt. Okay, this is, so we have 3t squared over 2 minus 5t from 0 to 3. Okay, and of course the rest is really easy. Just plug in 3 in all of this. 3 times 3 squared over 2 minus 15, or 5 times 3. And then the other piece is just 0. So we leave it out. So after simplifying, you should get minus 3 over 2. So we have a displacement of 3 over 2 in the negative direction. Okay, so part B, it says find the distance. So I just want to, so that, and this is find the distance. By the particle during the time interval. Okay, so distance is always positive. Okay, so let's then calculate the, and I'll try to fit this on one page, so please bear with me if this piece gets a little bit crowded here on this page. So we have the absolute value going from 0 to 3 of the absolute value of 3t minus 5 dt. Let's apply the absolute value definition. So we get, so absolute value of 3t minus 5 is equal to 3t minus 5 if 3t minus 5 is greater than or equal to 0 and equals minus, let me put that here, minus 3t minus 5 if 3t minus 5 is less than 0. So of course that will lead to this result. We have 3t minus 5 if, solve for t from this inequality, we get t greater than or equal to 5 over 3. And this one, let's distribute this. We get 5 minus, distribute the negative. We get positive 5 minus 3t is our expression inside the integral if t, solve for it here, is less than 5 over 3. Okay? So then we can integrate this absolute value. What do we get? We get this is equal to integral from 0 to 5 over 3 of, when that happens, this is our expression, 5 minus 3. This 5 minus 3t, right? So 5 minus 3t dt plus from 5 over 3 to 3, right? That's our interval. This is our interval from 0 to 3. So 5 over 3 to 3, or t greater than 5 over 3, this is our expression, 3t minus 5 dt. Okay? So then the rest is really easy. We can just integrate. We have 5t minus 3t squared over 2, 5 over 3, 0, plus, I'm just, I know I'm going through this fast, but this is pretty easy. I'm sure you'll have no problem following this. Minus 5t going from 5 third to 3, right? Just double checking, making sure that I have it. Okay. So then after that, then we end up with, so these are the quantities we should end up with, 25 third minus 3 halves times 25 over 9 after you plug in 5 third. The 0 part drops out, so let's ignore that. So simply plus, plug in the 3, and we get 27 9 times 3 over 20, 27 over 2 minus 15, right? 3 times 5. And then minus, plug in 5/3 for all of that. We get 3/2 times 25 over 9 minus 25 over 3. Okay, like that. So this is all just algebraic manipulation, and after that, hopefully we all agree that this is 41 over 6 meters, right? This is, since they gave us the, everything was in meters and seconds, so this would be distance in meters of displacement, or distance traveled, the distance traveled in meters over 3 seconds. Okay, so I hope this section and our work here made it a little more clear how to handle definite integrals. And I thank you for watching the video until this point. And for now, have a nice day, and I hope to see you again next time.